In section 9.4, we're going to be looking at the idea of growing at a rate proportional to something. Our differential equations y prime equals ky. And this is going to represent exponential growth and decay. So to start out, let's look at, just by inspection or guessing, what the solutions are going to be to the following three differential equations. Noting that the first one is something that we saw in the first week of material for this section, for this chapter. So the differential equation y prime equals y, the solution is a function. Solution is a function. We're going to call that y is equal to a function of x. So we're looking for some function of x that satisfies the property that when you take the derivative of that function, you get the original function back, y prime equals y. And we saw in the last week's material that the solution e to the x works, as the derivative of e to the x is e to the x. And in fact, we actually went one step further. We said that this was a particular solution. And the general solution, which is what we're going to be focusing on more, was y equal to c e to the x. If you take a constant times e to the x and you take the derivative of that, you still get c times e to the x. So now let's look at something a little more complicated than that, and that is y prime equals 2y. And let's talk about what the solution is going to be there. The thing to take away from this is that this is going to look something like e to the x. And let's just try e to the x and let's see if this works. So when you take the derivative of e to the x, you get e to the x. And we need that to be instead 2 times the function that we are dealing with. So this doesn't work here because we have 1 times that function. So let's instead, we're just going to say, is there a function like e to the x that when I take its derivative, I get 2 times that function? And this is going to be e to the 2x. When you take the derivative of e to the 2x, you get e to the 2x itself times the derivative of the inside function, 2x, and that is 2e to the 2x. And again, note that this is the derivative of y here, and this is 2 times the function y. So the derivative of y is 2 times y. The general solution that we are looking for here is y is equal to any constant times e to the 2x, and that is a solution, a general solution to the differential equation. If we take that one step further, we can say that a general solution to this third and our more general kind of differential equation here is going to be y equal to a constant c times e to the kx, where k can be any constant. We talked about this as the constant of proportionality. We're going to be talking about growing at a rate proportional to something, and that rate is represented by k. And now we know what the solution is going to be in general for those differential equations. So let's say that explicitly. So in this section, we're going to be looking almost exclusively at differential equations of the form y prime equals ky. We're going to have a little bit of added difficulty there. We'll see that in the next video, but that's basically what we're going to be dealing with. The general solution to that differential equation is going to be y equals c e to the kt. Notice that we're doing t here instead of x. And there's a reason why we're going to be writing that, because in most application problems, the independent variable x is going to be represented by time. So we're going to use t most of the time here. And then the new thing past this is that this is representative of exponential growth or decay. In a pre-algebra course, or not, sorry, not pre-algebra, pre-calculus course, you may look at functions of this form, y equals c e to the kt. And you'll know that if k is positive, that represents exponential growth, a function that might look like this. And if k is less than 0, you might have something like exponential decay, something that looks like this, where it's getting closer and closer to 0 as x gets bigger. And it's also important to note that this value c is very important, as it is the value of y when t equals 0. This is going to be our initial value in our problems, what we're starting with, our starting value. And again, know that if you have y equal to c e to the k times 0, this is going to give you y equals c e to the 0, and that's just 1, so you're going to get y equals c. So when you plug in t equals 0, you get an output of c. Y of 0 is equal to c. This would be the initial condition. And we'll see that in some application problems in the next video. All right. So let's think about what the graph of these solutions are going to be, because note that for different c values, we have different solutions, and they can look different depending on what we have here. So note that we have y prime equals ky, and our solution again is c e to the kt, and this time we are saying that k is positive, greater than 0. So if that's the case, if we try to plug in some different c values, we get these exponential graphs. So if we plug in c equals 1, we get this graph right here, and it would keep on going in an exponential form forever. And that is the function, right? This is y equal to 1 times e to the kt. And we can do that for c equals 2, c equals 3, any c value in between. And note that if you have negative c values, negative constants, those are reflections over the t-axis, and they're going to be going in the downwards direction. There is one solution that's not graphed here that's very important, and that is what happens when c is equal to 0. And that is this solution right here. So this is the one corresponding to c equals 0. And note that that's not a very interesting solution, as that's going to be 0 times e to the kt, which is just y equals 0. We're going to see in the next section what's important about this particular solution, and we're going to call this the equilibrium solution of this general solution. Let's see what happens when k is less than 0. So note that this is exponential growth. Even though it's exponential growth, even if we're talking about going down, right, to negative infinity, we're growing to negative infinity. So that is thought of as growth. If k is less than 0, we still have the same solution. Here we have e to the negative kt. So sorry, I should say if this is the differential equation, y prime equals negative ky, where k is a positive constant, we have a negative out there, or that's the same thing as saying your k is negative. You have this solution, and this is going to represent exponential decay. And just as we can see different solutions for different c values, these are all going to approach 0 as t gets bigger and bigger. And there is one solution that we did not draw, and that is the equilibrium solution, where we have c equal to 0. And again, that's the solution, just y equals 0, whereas opposed to maybe this one right here is y equals negative 3 e to the negative kt. All right, so exponential growth, exponential decay, depending on if our rate that we are growing at is positive or negative. That's going to determine whether we have exponential growth or decay. So let's look at a particular example now. We'll deal with a bunch of application problems in the next video. But right now, let's just consider the differential equation, this y prime equals 2y. And before we find the general solution, which we already did in this video, before we do that, let's talk about what the value of 2 actually represents. 2 here is the constant of proportionality. And since 2 is positive, this system is going to represent exponential growth. In the context of a word problem, this would be growing at a rate of 200% of the original quantity. Keyword here is the growing at a rate of 200%. Everything we're going to deal here with rates is going to be in decimal form. So 2, if we move the decimal point over 2 spots, that's indicative of a 200%. So if we had a word problem that says growing at a rate of 200% of the original population or original quantity or whatever we're dealing with, that would be our differential equation. We already found the general solution of this differential equation. This is y equal to a constant c times e to the 2t. This is a general solution because it represents all solutions with that value of c depicting different particular solutions. So in the third part, find the particular solution of the equation with y equals 1 and t equals 3. Again, this is what we call our initial condition. Or equivalently, we could write this as y of 3 equals 1. This is our t value, and this is our y value. So we can say that, note that we could write this as y of t is equal to c e to the 2t. It's not a way of doing that, but if we use our y and t values, we can say that y is equal to 1. So we have 1 is equal to c e to the 2 times 3. That means that we have 1 is equal to c e to the 6th. E to the 6th is just a constant, so we can say that c is going to be 1 over e to the 6th, or e to the negative 6. So we could write our particular solution as y equal to e to the negative 6 times e to the 2t. And one final note, we could write this as combining those exponents, e to the 2t minus 6. But we'll just focus on this first way that we wrote it. A constant times e to the 2t. Since that constant is positive, this will go off to positive infinity, since 2 is positive as well. In the next video, we're going to look at different application problems with this idea, and then we're going to expand the differential equation in section 9.5.